hear more of them. So Professor Mandal is here with us already, and
Then 3 more seconds.
yeah, it's so. Yes. Dr. Bindal, you could switch on your video if you want. Okay.
Ma'am, we are live.
Okay. So it's again a pleasure for me to introduce our next speaker, Professor Mandal, to the attendees. I'm sure the attendees here are the ones who are regular and know Professor Mandal by now, who has been teaching us nuclear physics. Professor Mandal has been employed at University of Delhi since 2005. There is some background noise. So there, okay, some background noise is there. Professor Mandal has been teaching in the Department of Physics and Astrophysics, University of Delhi since 2005, and since 2011 he's working as a professor there. His research interests include nuclear structure of exotic nuclei, reaction dynamics, multinucleon transport, and superfluidity in nuclear physics. Nuclear instrumentation, gamma ray tracking, pulse shape analysis, nuclear T factor, gas detectors, and nuclear astrophysics. So he's also PI of several national as well as international research projects which are done or which are performed as with India as a collaborator, such as the Fair New Star project and so on. He's also the PI of the Indian National Gamma Ray Array, INGA, and neutron detectors. He was ex-joint secretary of Indian Physics Association. Presently, he is helping us to understand business level nuclear physics. Professor Mandal, there is some background noise coming from your end. Could you please check something? Okay, so I now invite Professor Mandal to kindly share his screen and deliver his talk. Something is stuck.
Hello? Hello, can you hear me? I cannot hear anything.
Can you hear me?
Yes, ma'am. Purita ma'am, we can hear you, but we cannot hear Samit sir.
So we take a minute and we sort this out immediately. Professor Mandal, can you please speak something?
Hello, can you hear me? Hello?
Yes. Please share your screen and you can start then. And also please switch on your video. Let us check.
It is automatically switch off and on, going on. I don't know, some problem maybe.
Okay, so please share your screen. We will then manage accordingly. Please share your screen. Dr. Bindal, I think we all should shut off our video and audio. And
see now.
yeah, but your voice is very unclear.
Hello, can you hear me? Hello? Hello,
Yes.
We
can hear you. Yes, please go ahead.
The sharing part. Can you see now?
We can see your screen as well and we can hear you. Voice is disturbed.
Then how is it run? Hello? Okay, okay students, so we are continuing with our shell model. The shell model what we are discussing. Last day we just discussed in one class actually the basic of the shell model and how one can calculate the spin parity. Obviously, I didn't talk about or I didn't show you the derivation part because it is not also possible. In one lecture and all the thing, maybe the two lectures, so you need a lot of, but you can do it in your home because all are quantum mechanics, so that's no problem. If you can, if you have your quantum mechanics books with you, so then immediately you can solve it because solving your shell model energy using the harmonic oscillator potential, that you can do it easily. So that's why I didn't show it in my lecture how one can do that one. That's why I just simply directly mentioned the energies level and how one can place the particle in different energy shells. Hello. So now we can see from the shell model. So what we discussed that the how we can find out the spin parity for the even nuclei. The spin parity for even nuclei, so that you know from the basic assumption says that the spin should be the zero because all neutrons or all protons the pair together separately, that the neutron should be paired with a neutron and the proton should be paired with a proton, and hence the total spin, if you look for the coupling of the two spin, then it should be gives you the zero value. Therefore, for even nuclei, we always say the spin parity for any nucleus as they are counted should be zero. But odd and even or odd number of neutrons or proton, vice versa, whatever. So the last unpaired neutron or a last unpaired proton will be responsible for the spin parity of the odd even odd nuclei. So, and there I show you the how to calculate the spin and their configuration. And also I mentioned because of the two different potential, for the neutron case we have only the nuclear force, for the proton case we have a nuclear force as well as you have a Coulombic force. So therefore the potential also a bit different. So therefore the single particle state also alter after some energy state that we already shown, like here shells and the neutron energy single particle levels. And here we mentioned after n equal to or total number of proton or total number of neutron equal to 50 gives the different configuration or different energy levels placing or spacing, whatever you say, for the proton case one type and the neutron case another type. So therefore, when you talk about the spin parity, you should be very careful whether your spin parity for particular nucleus is mainly for the neutron configuration or the proton configuration. It is for the neutron configuration, then you will get the spin parity one shot and one type, and for the neutron configuration, you will get the spin parity another type that we last time we discussed. And how one can write the configuration, that I also show. This is a convention in the nuclear physics. You should write a particular way of particular
बोलेंगे क्योंकि अभी फिर साउंड खराब करने का मतलब नहीं, समझ गई मैं क्यों निकल रही हूँ.
Hello, can you hear me? Okay. Hello. It is audible?
Yes, sir, it is audible, sir. Please continue.
Okay. So now, the for the odd even case, like for here. So odd and sorry. Odd and even case we mentioned, or the even or odd case that we mentioned. Now, what about the odd case? What will be the spin parity if we consider the? So obviously, you can see then who will be responsible for the spin parity? So therefore, this extreme single particle shell model that we are discussing at the present moment is somehow is not able to explain the spin parity for the ordered nuclei. So therefore, uh, therefore, then you can say the based on the extreme single particle symmetrical model, we cannot explain because say I am considering a nuclei which is a maybe this can be the carbon nitrogen. So the nitrogen 7, 14, then 16 nitrogen. So consider the 16 nitrogen, it's a 7, 16, sorry, 14 nitrogen, I'm sorry. 14 nitrogen, you have a 7 neutron and the 7 proton. 7 proton here and 7 neutron. Then what will be the spin and parity of this particular nuclei? So you can see the how many neutrons or protons are there. So it is 7. So then I can place 2 neutron here, 2 proton here. So first I go for the maybe the neutron configuration, 2 neutron. Then here I can place 4. So that will 1, 2, 3, 4. That is 1, 2, 3, 4, 5, 6. Still 3, 4, and then 1 is here. So therefore, 1 unpaired proton and 1 unpaired neutron. Both are responsible for the spin and parity. So in that case, what will be the spin parity? So therefore, the few possibilities here. So there are one can find one of the possibilities generally called the Nordheim rule. So it is called the Nordheim rule or Nordheim's rule. It is called the Nordheim's rule. What he says that if the total spin of this particular system, that if the total spin if the total spin for all the neutronic system, what will be the spin for all the neutronic system? That here you can see the 2 are already 0. This is 0. This is 0. That means last neutron. So this spin is half. So for the neutronic spin, or the Jn equal to half. Similarly, for proton case also, this is paired. This is 2 are paired 2, and this is unpaired. So the also half. These two. These two, the neutron spin and the proton spin.
Sir, excuse
yes.
me, sir. Sir, yeah. Can you please shut down your video and audio once for a minute and then start again because your voice is breaking.
Okay. Let me. So I am coming out. Stop my sharing. Fine.
Audio and video as well, sir.
Just a minute where it is. Just try to find it out where it is. Where is concept? I shut down.
Hello, attendees, please wait for a minute. Sir will join again so that we can have a clear voice and, smooth presentation. So have patience for a minute. He will be joining in a minute.
Hello, can you hear me now?
Yes, sir, we can hear you and it's clear.
Maybe I just switch up my videos. Maybe problem with the bandwidth.
Okay, sir.
So okay, this is one to show the notification. This is application window. Yeah. Hello.
Yes, sir.
Oh, oh, this is somewhere. Anyway, so what? Acha, this is already displaced. Something, everything is displaced. Anyway, then I have to redraw. Anyway, what we are discussing that anyway we should not this one. This is gone. So we have here, 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 and here, 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 1, 2, and this. So neutron J n equal to half and Jp equal to half. The neutron neutron spin and the proton spin. So now what the rules say? There is a two type of what he mentioned. These Nordheim's. The one is called the strong rule. Strong rule. And the strong rule say if the total J, because this is a two angular momentum, J is a neutron angular momentum and this is a proton angular momentum. And these two angular momentum, if you add, because this is two are the vector quantity, so you have to add vectorically. So you have to go for the angular momentum coupling scheme. So here, so therefore he says that Nordheim says that for if the J equal to my total J is equal to the mod of J, you can say the P minus Jn, if it will hold, if the J equal to mod of Jpn, or you can say this is the value of the J, the value of the total angular momentum should be J when Jp minus J, if, if we consider the maybe Jp equal to say the LP plus minus half, and LP is the angular momentum. The Jp is your, this is your Jp that we discussed long back, that J equal to your L plus S. It is a total spin, and that L is the angular momentum. This is azimuthal angular momentum. If the azimuthal angular momentum of the proton is this is the thing, plus minus half, and the Jn equal to ln minus plus half. Then it will follow the strong rule. In that case, the J equal to the mod of Jp minus Jn. So this is the strong rule what he suggested, the Nordheim. And there is another rule which is called the weak rule. So where should I write? Maybe in down. Go down. So then another rule, that is the weak rule, which says the J, the value of J should be lie in between the Jp minus Jn, J, and this is equal to your maybe the Jp. Oh, sorry. Where is gone? Just a minute. I have to take this eraser and go back to the 8. What I this one I just sorry, just a minute. Yeah, I, okay. So it's a mod of J minus P, and this is the less than Jp plus Jn. So it lies between this one, if I'm correct, I'm writing correctly. So then I should get, sorry, if so not I say, so if the Jp, if the Jp equal to Lp plus half, or Jn equal to Ln plus half. You can have another way of writing. So the strong rule, you can write the strong rule in this way also. The strong rule, you can write if Lp plus Jp plus Ln plus Jn is even, then you can go for the strong rule. That means J should be vary this one, and if weak rule will be valid, weak rule will be valid, then in that case the Lp plus Jp plus Ln plus Jn is odd. So the both you can use both the techniques you can use, and then you can go for the weak rules. So that means for the weak rule case, you can see that J value can have a all possible Jp plus Jn. That means here you can see for our case the nitrogen 17. So it's a 7 neutron and the 7 proton. So then try to find out what will be the spin parity. So if you look at the spin parity, Jp will be the half. This is also the half. So and both are following this rule. That means they are Lp, because for neutron case, what will be the L value here? Because you can see the L is in the p state. That means L equal to 1. P equal to, the neutrons are staying at the p state. L equal to 1. That means I can say for nitrogen, for 14 nitrogen case, so my Lp and Lp equal to proton case also 1, and it is 1, and you can see the half. So that means the spin value is a half. Sp equal to half. So then Jp I should get one possibility 3 by 2 and half. So but here that means the value should be the Lp minus half. So that's why you are getting Jp equal to half. The similar for the Ln equal to half and the Sn equal to half. So and Jn equal to Ln minus half. That's why your Jn equal to half what you are getting. Otherwise, if you get the 3 by 2, but you are placing at the half. So therefore, the Jn value half and half. So both are, you can see the Ln minus half and the Lp minus half. So this rule, because it can be the both are same sign, L equal L plus minus or the plus minus both. But other case, if these two are the revert, then you go for the strong case. So but here now you can see with that, then have all possible the angular momentum Jp minus Jn, the half minus half equal to 0. And then what is the Jp and add? This is a 1. So therefore I have two possible angular momentum, total angular momentum 0 and 1. So now nitrogen system can have both possibility, the 0 and half. Now what will be the parity? Parity should be then, as you know, parity should the parity should equal to minus 1 by Lp plus Ln. That is the parity for my odd even system. So Lp and Ln, this gives you half and half. That means 1. Lp and L, sorry, 2 here. Lp equal to 1 and the Ln equal to 1. That is 2. So that means is equal to positive parity state. So therefore, the spin parity for 14 nitrogen, it should be the 0 plus or the or even you can say the 1 plus. These are two possibilities there. Now, which one will be the correct one? 0 plus or the 1 plus? But then, how do I know? So experimentally it was observed the 1 plus is the correct answer. So now this 1 plus parity, spin and parity for nitrogen 14 case. This you can, then you have to introduce, to explain this one, to introduce the concept of the isospin. Now you can see for isospin case, here I have to now talk about a little bit about the wave function. So now, as we mentioned earlier, that each wave function, because this particular state has a particular wave function, single particle, the energy state has a particular wave function, and we define this wave function by psi. Now, this psi is depends on the three quantity that I already mentioned. If you don't go in the details, the minimum three quantity. One is the radius or the position. Other is your spin or sigma, I can say, and other is the tau or the isospin. My total wave function is a function of the three quantity at the present moment. So the position, the spin, and the isospin. This one we can write in this fashion also, the psi r. Then you can write the spin wave function. This is in this form, and other one is your this one maybe the something, yeah, some tau. So this is part, because it depends on the radius. This is the space part, and this is the spin. This is the space. This is the spin, and this is your isospin part. This is three part of the wave function. And now this particular state also follow, or the when you are placing your particles, you also should remember that you because those are the particles of fermion, so therefore you should follow the Pauli's exclusion, the principle. So that means I can put only one particle in one state. And now you can see that the total wave function and the total wave function should be symmetric. So in this particular say the 1s state, the wave function should symmetric. So if you put any exchange of the under exchange of the particle, or under the exchange of the spin, or under the exchange of the isospin, my total wave function should be the symmetric. For the S case. For the P case, because the P case may not be symmetric, because it is the L value is different. For this particular case, I can consider this total wave function should be symmetric. So therefore, my wave part, this is the space part. If I can forget it, because this is if I system is spherically symmetric, so therefore this part is always the symmetric part. So therefore, these two quantity will be responsible for the antisymmetrization, because your Pauli's exclusion principle requires your wave function should be antisymmetric. So how do you make these two whole wave function antisymmetric? Because this part is for spherically symmetric nuclei, or we can consider this part is the symmetric part, but then this spin part or this isospin part should be antisymmetric. So for the spin part, if you want to take the spin part antisymmetric, that means I have a two particle, one particle the spin is half, and then other particle spin should be minus half. Okay, so then I can see the wave function can be, if I exchange the particle, so under the exchange of the particle, the wave function then remain antisymmetric. And similarly for the isospin, if the isospin, the third component of the isospin, if I have a plus half, the exchange of the particle isospin, if I exchange the particles isospin, then the wave function remain the antisymmetric. Now, to make the total wave function antisymmetric, so then what you can see here that if I consider the wave function for this state and this state, total wave function should be antisymmetric for the proton and neutron together. So then how we can make the total wave function antisymmetric? So for space parts, forget about this is symmetric one, and the spin part. The spin part, you can see the neutron spin and the proton spin. They are in the opposite direction. If they stay in the opposite direction, if the neutron spin in the proton spin in the down direction, then I can make the antisymmetric. Okay, wave function, because they. But if these two are in the same direction, if both are pointing the same direction, then if you take the interchange the spin, then obviously this part will remain the symmetric. So then the isospin part. So then what will be the isospin? Then that means the third component isospin should have a different value. One is the proton and other is the neutron. So then in the proton and the neutron, this isospin spin value anyhow, they are in the opposites, opposite here. So then that means one neutron case, as per our convention for this class, I mentioned, though it is not nuclear physics, we don't use this convention. For this class, we mentioned this is the neutron isospin, sorry, proton isospin, and this is for the neutron isospin. So neutron isospin, third component isospin, the half, which represent the proton, and the minus, which represent the neutron. So they are already, if I interchange, then obviously I will get the antisymmetric wave function. So therefore, isosymmetric part is always I am getting the isosymmetric component. So therefore, the spin part, this is this part, that means antisymmetric. Now, if both are in the opposite direction, then I get the antisymmetric. So therefore, this antisymmetric give me the symmetric. So therefore, the total thing will be symmetric, and that we don't need. So this is symmetric wave function. This is antisymmetric wave function. So therefore, this part should be the symmetric wave function. To make this spin symmetric wave function, so therefore the total S value should be in the up direction. The spin of the proton as well as the neutron should be in the up direction. If the spin is the up direction, that you can see here. So this particular state, this is the particular state. If I take the SP and SN, this will give me the total value is equal to half plus half. You have to do it in the vectorically. You have to add it. Then you will get the half plus half. But and then your sigma is there, so I am not writing the sigma part. So anyway. So this is the spin part, and the isospin, the third component, as a half, and I have got minus half, so I am getting the 0. So the isospin state for this system gives me the 0 value. So isospin is 0, and the spin value 1 plus 1 is the plus 1. That means the minimum spin, total spin, then it should be valid for the 1 plus, because the minimum spin what I can see from the here, it will give me the 1 value. Otherwise, I cannot produce this state. If we take the 0 plus state, if the 0 is state, then the isospin gives you 0, but the spin part is 0, because then I have to take the opposite direction of the spin. And in that case, so therefore I should not consider this 0 contribution for the spin in my calculation. So therefore, the only possible answer will be the plus 1. So similarly, you can explain several other case like a 10 boron, which is high 5. The similar case, a similar way you can explain based on the isospin logic that why the spin, what is the mean ground state spin for boron 5 also. Similarly, other nucleus you can explain. But this is if we use the extreme single particle shell model. But if you go for the many particle shell model, obviously this type of logic is not required. Fine. So with that, so maybe this will give you some idea for the odd even how to calculate the spin and parity for even, odd even, and odd nuclei. Okay. So now, if it is clear to you, so then we can proceed for the next part. Next part is the excited state. how one can get the spin parity value for excited state of a particular nuclei. Oh, sorry. Well, maybe. Oh, this is some space available. Yeah. Oh, no. Yeah. How we can calculate the, say, the excited state of a particular nucleus. So how one can calculate? Maybe I can try to find out some. This one will be fine. Say I want to calculate the spin parity of a maybe 17 oxygen. 17 oxygen. It is a 8 and 9. 8 number of proton, and this is the neutron. So then the spin parity for this one will be dictated by the unpaired neutron present in this nucleus, the ground state spin parity. And what will be the ground state spin parity? So I can write in the little bit in the configured way, that is a 1s half. I put 2 particle there, then the 1p 3 by 2, I can put 4 particle there, then 1p half, I can place the 2 particle, so the 2, 2, 4, then 8, and then the last one go to the d5 by 2. So then it will be the 1d, or maybe you can write here 1d 5 by 2, and I am placing only 1 particle there. Okay, this is my the ground state spin, and the spin is j, then j equal to, then this is 3 5 by 2, and the parity, because the d is my L equal to 2, angular momentum for the d state is 2, and then the parity will be the square of this one. So then it will be the, oh, this I should not, this is should be the plus. This is a conventional way of writing the I should not put a bracket here, so maybe I just drop that one. Yeah. So this is the spin parity of my system, and this is the standard way of writing the spin parity for a particular nucleus. Don't put a bracket here, then it will mess up. And this is the way of writing the configuration of a particular nucleonic state in a shell model configuration. Okay. And now you can see this is a spin parity for the ground state. So I can say this is the ground state spin parity. Now, what will be the excited state? Here I can say the proton, I am giving, say, the neutron here, here, 4, 1, 2, and 1. So now you can see that if you can supply small amount, and for the neutron case, the proton case, everything is closed. The proton case I am putting here, proton case 1, 2, 3, 4, and these 2. And you can see this is a compact system because this is a magic number. So it will be, and you can see if you want to excite, now you give some energy to the system. The proton will be very difficult to excite because you need the large amount of energy to excite this state. Because this amount of energy, if you can supply, so then this proton can move here to here. But then if you look at the neutron configuration, one neutron is already sitting here. And if you give small amount of energy, then it can excite to here. If you give little bit more, it can excite here. And if you give little bit more, it can go here also. It can go in the higher level. So it depends upon how much energy you are supplying to the system. Accordingly, you can excite your single particle state from its higher energy levels. Any levels it can go. That depends on how much energy is supplied. Say that I am supplying the minimum amount of energy, which is maybe the energy difference between these two levels. A few kV energy I am supplying. So then this neutron can move here to here. But if you supply more than energy, then not only this one, it's may possible if you supply say energy which is that defines between this energy or more than this energy, then you have a possibility also lift up or excite on present here. You can move arrow. So therefore, you will be very careful when you can see this type of question. We are putting the excitation energy, and then I try to excite, then write down the configuration for what are the possible state of the nucleus if I excite the nuclei. So this is some type of vague question. So then you have to specify what is the energy difference and how much energy is supplying to the system. Then you can consider those questions are perfect question. Otherwise, there is no meaning. I am seeing the several the question paper. They are asking what are the excited state are possible without specifying the energy level, and also the how much energy I am supplying to the system. So therefore, then you have to see the what type of question they are asking. If they are asking with specific the energy difference is mentioned and also the level spacings are mentioned, then you will have a chance to answer such type of question. So now if I specified you that okay, this only the I am supplying this amount of energy, say the delta E amount of energy, which may be the Q the few kilovolt order. So then this neutron can be moved from this state and this state. So and if it is moved from this d5 by 2 state to the S half state, then you will get the spin parity will be the first exercise state spin parity can be then the half. And S is plus, so the plus. And the second state it can give little bit more energy, maybe the delta E1 energy if you supply, then it will be the then D3 by 2, so the spin parity will be 3 by 2 and so on. So therefore, this single particle, how much you can energy you have to know to answer the excited state energy and excited state the spin parity. Otherwise, it will be very difficult to tell you. So therefore, the excited state spin parity depends upon how much energy you will supply to the system and compared to the single particle energy difference between this single particle levels. So therefore, you will be very careful that what type of question the things are asking in your paper. Okay. So this way, then now if you give the more energy, there's a possibility that both the particle can move in the higher level. So then you have a different configuration, and then you have to find out if you put all the two particles here. This is possible. Then you have a 3 particle in one level, and then the spin parity obviously dictated by this one. But here you have a 2 hole, but doesn't matter. But the spin parity of the system will be dictated by the last unpaired neutron present in this. So in that case, spin parity for excited state will be the 5 by 2. I'm saying that when you look for the excited state, you should know how much energy you are supplying to the system. Okay? So this way you can calculate the excited state, the spin parity. Fine. So there is a several way you can do it. This is the very simple way one can do it based on the extreme single particle shell model. Okay. So now, if it is clear, so then we can move to the other part. That is the magnetic moment part. How you can calculate if you know the spin parity of the system, then how one can calculate the magnetic moment of a particular system. And also I mentioned in one of my lecture, the beginning lecture, that I will talk about this Smith, the magnetic moment, how to calculate the magnetic moment for saying based on the single particle shell model. This part at that time I didn't cover because now you have some idea of the shell model. So now I can, and you know how to calculate the spin parity. So now one can calculate the magnetic moment of a particular the nucleus. Maybe Professor what is called Professor Gautam Ganguly, he already mentioned that how to calculate the spin parity. He calculated how the magnetic moment for neutron system. But now here we try to calculate the spin parity for any nucleus. So any nucleus means whatever nucleus, because the even what will be the value of the even nucleus, what will be the value of the odd even, or what will be the odd nucleus, that we can now discuss about it a bit. Let's see, I just what I have thought about discussing. Let's see first find it out. Yeah. Yeah, that's called the sweep model. Yeah. So first we talk about little bit about the sweep model. Last time in my first or second lecture, I mentioned how to calculate the magnetic moment of a nucleus, and this magnetic moment of a nucleus. Maybe I can go to the next some page. Yeah. So last time what I showed you the magnetic moment of a the nucleus. This is a mu. I made it right. Oh, it's not writing. Yeah. Last time what we wrote, mu equal to h. E8 is the charge of a your charge of a nucleus, and this is equal to 2 mass of a nucleus. It can be the neutron, it can be the proton. So the mass of a nucleus, sorry, this is equal to this is equal to this is equal to summation k equal to 1 to z, and then you have a lk. K stand for, yeah, lk means your whatever. Sorry. And this is for the gp, is your the g factor, and this is the spin value. This is angular momentum and the spin angular momentum, and then this is gn that from the last, I think the second lecture or the first lecture, I don't remember, there why I showed you that this is coming like that, and this is sk. This is my the magnetic moment, what I mentioned earlier. Now I try to calculate, if I try to calculate the magnetic moment, for if I consider for simple case, for the odd nucleon, because odd nucleon will be easy because the last unpaired neutron and proton is responsible for spin parity. So the odd even nucleus, and whether odd even nucleus or even odd nucleus, that is the easy case. And say that the angular momentum for such nucleus is the angular momentum of say L, and total spin, nuclear spin, is a J. That is our basic definition, and so then J equal to L plus S, that we know. And also we consider the G factor for a particular J value is a Gj. So this is a G factor for the proton and the G factor for the neutron, and G factor for the for particular nucleus with the angular momentum, nuclear angular momentum or nuclear spin J equal to Gj. That's what we consider. So therefore the magnetic moment mu, then I can write as the GL L plus GS S equal to Gj into J. No problem, because this is a revolution from the angular. This is the angular part, and this is for the spin part. For the simple case. So now if I multiply both the sides, if I multiply both the side, mu dot J, take a dot product of this J. So then it should be the GLL dot J plus GSS dot J and GJ and the J square. J and J square, that's why I'm putting the vector sum here. But these two are the vector quantity. So now I just subtracting these two equation from one to another, and then I will get easily the L dot J small j, sorry, L dot small j equal to J square into S dot J. And then from this equation, then from this equation, then we can get the J square equal to GL J square plus, in fact you can do it what I am doing. This is easy, huh? S dot J, and then is basically will give you the J equal to GL plus GS minus GL S dot J by J square. You will get it from here. You can see the J, I just put it here, and then you take the expectation value of this one. Huh? If you take the expectation value of this one, then ultimately I'm just going to the final result. If you take the expectation value, so the S dot J and sorry, this is the J square. I should be careful about this. J square. This will give you the two value. One is the 1 by 2L plus 1 for J equal to L plus half, and other value you will get minus 1 by 2L plus 1 for J equal to L minus half. So you get the two expectation value. For this one is a so that's why I'm not doing this one. So then you can place it here. So then you can put those values. So then immediately you can get the GJ value will be equal to GL plus GS minus GL, then 2L plus 1 for this is if L J equal to L plus half. This is L plus half, and then other value you will get the GL minus GS minus GL 1 over 2L plus 1 for J equal to if the L minus half. So therefore you get the two value of the GI for these two things. Now if we know the L value and the GS and the GL value, so then immediately you have G factor GL, and when you calculate the GL, then immediately the G, because the G, this value we are calculating from here, and then the J value we are getting from the shell model, then immediately you can get this magnetic moment. So that is very simple. So therefore you have to know the GJ value and the GJ value, and now by experimentally we know what is the GS value of the order of 5.585 nm nuclear magneton, and and for GL value equal to 1 nm, and this is for proton case. This is for the proton case. So I know from the experiment that GS value equal to 5 nuclear magneton, and the GL for the proton is equal to 1 nuclear magneton. And similarly for the GN value, we can get for the Gn value for the neutron case. This is for the neutron case. This is for the proton case. This part is my proton case, and this here, this side I am writing the neutron case. The neutron case, the Gs value value equal to minus 3.826 nano. Nuclear magnetron. This is the all experimental value, and the GL value equal to 0 because there is no orbital angular momentum for neutron. So therefore, it equal to GL equal to 0. So now you know the GL and GS value for the neutron. So then you can plug in here. Then you can find what is the value of the GS for particular value of L. So the GL, why it is going out, I don't know. So therefore you can calculate this one, then find out this one from the shell model. This is also L and the J value we have to find out from the shell model, and the mu G and the G from through this experimental value. Then you can know what will be the value of the mu. So there is a small table is there. You can available most of the book. The small table. So that table shows that say the for particular value of the J, for particular value of the J, the L, I have two possibility of L half and L minus half. Corresponding by magnetic moment. So magnetic moment I can get. So I can write in terms of a nuclear magneton. So therefore write that. And if the nucleus contain the odd neutron number, odd neutron number or odd proton number, odd neutron and the odd proton number, then the value will be like that. This is in most of the books you will find this is some table is given, and then they can show this one. For the neutron case, it will be generally the minus 1.913. Or proton case, it comes should be the J plus around I think 2.2 or something, 2.23 or something like that. You can check it. For this value will be come out will be the plus 1.91. Then the extra term generally comes. This is J, and to J plus 1, the extra term generally comes, and here you will get equal to J minus 2.23, and then this extra term, this is equal to J into the J plus 1. So this thing obviously we will get from the what I did here. So based on this calculation, so can be summarized in this table. So therefore, if you can remember this table, so then immediately from the shell model, you know what will be the value of the odd proton or odd neutron. Then immediately you can see, you can calculate the magnetic, the moment of a particular nucleus based on a single particle, the shell model. Fine. So with that, maybe we can complete our shell model part, extreme single particle shell model part very quickly, and you can see the mostly you will get a question from any type of exam, magnetic moment or magnetic moment basically, and then define the excited state and like this. So most of your whether it is in the your MSc level or it is in the JS or whether it is in the what is called the NET exam. So similar. So you'll get a lot of questions based on this this thing. And therefore, the one thing you should remember this table, so then it will be easy for you. And also, you should remember that I mentioned there's a spin parity. The spin parity for a nucleus which is having the spin parity of this level scheme. If you remember, and you should remember if they are giving the 50 above nucleus to find out the neutron and proton number, then you should be very, very careful about these two configuration, proton configuration and neutron configuration. After Up to 50 you have no problem, but after 50 you should be very careful about which configuration, which configuration is responsible for the spin parity, and accordingly you have to write down the proper spin parity for the neutron, because here the neutron and proton the cell structure is different, so therefore you should be careful about this one. Now, because you can see one of the I think your NET exam, there's asked for the I think ASP 51. So 51 is the proton number, so their spin parity will be different. And if it is some other thing, say the some 51 number present, so then the spin parity will be different. So that thing will be very, very careful. Okay. With that, I can stop, so that you can, if any questions are there, so that I can take up those questions. So, okay. Let's see any questions. Can I able to see those things? Where is? Is there no questions or stop sharing? Okay, sir, can we get the effect of external magnetic field in NMR using this procedure? This is the extreme single particle, and we are not talking about the external magnetic field here. We are talking about the internal magnetic field. Okay, the external magnetic field will be different things. So then there is several other contribution comes. So maybe in the quantum mechanics you can learn a bit, because you have to need a little bit more quantum mechanics here to understand this magnetic resonance business. So may not be, this is the forum, I may not be able to explain at the present moment, because I need a little bit more little bit to mathematical tool to explain this one. Okay. So I don't find any questions here. Okay, then we can stop. And last time we had few questions. I don't know whether from this forum or maybe from the other students, so that I'm not sure about. So if you have any other things to, you can ask me anything. So no problem as such. But there is something like one more explanation, because the different involved along the different axes. But I don't think so. Anyway, but those questions, maybe it was, I don't know, it will be relevant here right now. Maybe then I can stop now if there is no further questions.
Sir, let's wait for a second for Punita ma'am. I think Pushpa ma'am is here. Yes.
Yes, thank you, sir. Thank you, Professor Manda. It is a wonderful talk, and to the participants.
Thank you.
Yeah, thank you so much.
Pushpa ma'am.
Yes.
Hello.
Bolo.
Ma'am, we cannot hear you clearly.
No. No. Take it. Can you hear me now?
Hello.
So thank you, Professor Mandal, and I think Dr. Savita, you can stop recording now.
Ma'am, I will stop now. Once you formally thank you, sir, then I will stop the recording.
Hello.
Hello.
Ma'am, shall I stop the recording or stop the live stream?
Yeah, that is what I'm saying.